Assalamualaikum and good afternoon. So today we will continue our lecture on design of beam. So for today lecture, I'm going to show you how to solve the problem involving distributed load, okay, involving the beam that's subjected to distributed load. Okay, so last week I already showed one example, how to analyze the beam when it is subjected to concentrated load. Okay, only concentrated load. Now we are analyzing the beam under distributed load. Okay, so as I mentioned last week, there are few type of distributed load, which is rectangular type distributed load. You also have the triangle type distributed load, and also trapezium type distributed load. But for today, I will show you how to solve one example that involving rectangular type distributed load. Okay, so I hope you still remember there are 4 steps to solve this kind of problem. Okay, so first is draw the overall free body diagram, and then convert the distributed load into equivalent concentrated load. And then the step number 2 is determine the reaction force, and then step number 4 is analyzing each section. For this case is section AC and also section BC, and last but not least is draw the free body diagram. Okay, draw the shear force and also bending moment diagram. Okay, so for the 4 step that I mentioned before, you can refer back from our last week lecture. Okay, so okay, let me read the question first. Draw the shearing force and bending moment diagram for the overhang beam shown below. Okay, so for this case, we just follow the 4 steps that we already discussed. Okay, the first step. Okay, sorry. Let me delete this one first. Okay, so let me get my pen. Okay, so for first step, draw free body diagram and convert, okay, distributed load to concentrated load. Okay, so you have a beam. Example, you have a beam here, beam ACB. Okay, and then because we have pin support here, so we replace by reaction force FA, and then at C we have the roller support, so we replace by the reaction force at C, and here is the point B. Okay, so this is the distributed load with 10 kilonewton per meter. So as I said, we have to convert distributed load into the concentrated load. So I convert into the concentrated load. So the magnitude for the concentrated load is 10 times 4. Okay, so because the distributed load is 10 kilonewton per meter, so the load is distributed along 4 meter. Okay, 3 plus 1. So the total magnitude will be 10 times 4, okay, which is equal to 40 kilonewton. Okay, 40 kilonewton. Okay, and then the load will be will be located at the centroid of the rectangle. Okay, so this is the rectangle. Okay, let's say this is the distributed load, and then here is 4 meter, and then here is 10 kilonewton. So the centroid will be at the middle. Okay, and the distance should be 2 meter, because this is the rectangle symmetry shape. Okay, so the centroid should be at the middle of the rectangle. So from here we know that the concentrated load will be acting 2 meter measure from point A. Okay, so this is our free body diagram. Okay, so don't forget here is 3 meter and also from C to B is 1 meter. Okay, so from this free body diagram, the step 2 is, okay, second step is determine the reaction force, which is for this case is FA and also FC. Okay, so how to determine the FA and FC? So you apply the static equilibrium equation, which is the summation of moment equal to 0 and also summation of force equal to 0. So we start with the summation of moment equal to 0 first. So let's take the moment at point A, and then let's assume so let's assume clockwise direction is positive. So from here we know that 40 times 2, which is 40 times 2, okay, the distance from concentrated load to the point A is 2 meter. Okay, and then minus FC times 3, C times 3 is equal to 0. So from here we can get the value of FC. FC is equal to 26.67 kilonewton. Okay, and then if we apply the summation of Fy, okay, upward is positive, the total must be equal to 0. So we get that minus 40, which is here, okay, plus Fa plus Fc is equal to 0. So since Fc equal to 26.67, so we know this value. So Fa is equal to 13.33 kilonewton. Okay, so now we finish at step 2, which is determine the reaction force. Now we proceed with the step number 3, which is analyzing for each section. So for this case we have a 2 section, which is AC and also CB. So we will analyze this section. Okay, so let me draw again, so that we can refer to the original problem. Okay, so FA we already calculated, which is equal to 13.33, and then we have we have FC, which is equal to 26.67, and then we have distributed load. Okay, distributed load, which is equal to 10 kilonewton per meter. Okay, now we analyze section AC. This is point B. Okay, so and then I will analyze from the left part of the beam. So for section AC, okay, so for section AC, section AC, so I draw the free body diagram, okay, which is we have the FA, which is equal to 13.33, and then of course we will have the internal shear force, because we do sectioning, so we will have the internal shear force and then internal bending moment Ms. Okay, and then we assume this distance is equal to S, and this is our distributed load. Okay, so we have distributed load 10 kilonewton per meter. Okay, and then to simplify the analysis, what we have to do is we have to convert the distributed load into concentrated load. So we redraw our free body diagram, and then we have here 13.33, and then we have Vx, and then we have Mx, and we convert distributed load into concentrated load. Okay, so because for section AC, okay, the distributed load is distributed along the beam for x, okay, for x distance. The total length that the force distributed is x. So the concentrated load will be 10x, okay, because the total distance is x. Okay, so for example, previously we have 10 kN per meter, but the distance is 4. So the magnitude of the concentrated load equal to 10 times 4. Okay, for this case, our concentrated load, our distributed load is distributed for x. Okay, for the distance x. So the magnitude will be 10 times x. Okay, times x. And we know that the concentrated load will be acting at the centroid. So for this case, the centroid will be x over 2, because the total distance is x. Centroid will be at the middle, so the half of the x is x over 2. Okay. Alright, so from this free body diagram, we can apply the summation of Fy upward is positive equal to 0, and then we can write that the Vx, okay, plus 10x minus 13.33 is equal to 0. Okay, so from this free body diagram, okay, right? So Vx is equal to 13.33 minus 10x. So that is the relationship between shear force and also distance x. Oh, okay. Before I proceed, for section AC, the x is valid from 0, which is point A, to the point C, AC, so from A to C. So x is valid from 0 to point C. Okay, point C is 3 meters. So 3 meters. So it's valid from 0 to 3 meters. Okay, so our equation here actually is valid only for the x in between 0 and 3. Okay, and then we will develop the equation for bending moment. So summation of moment at point x, let's say in this direction is positive, must be equal to 0. So we can write the equation where the mx plus, okay, 10x, okay, 10. Okay, so we are taking the moment at this point. So we get mx, and then 10x times the distance, okay, from this point to point here, okay, which is x over 2, because this is also x over 2. So time x over 2, and then minus 13.33, this force, okay, time x. So the distance from point A to here is x. So I put x equal to 0. So from here we get the relationship between bending moment and also x, which is ms is equal to 13.33 x, okay, minus 5x squared. Okay, so from here what we can see is this is the linear relationship. Okay, linear relationship. This is the quadratic relationship. Okay, relationship. Now we already have the relationship between the shear force and also x, and also bending moment and x. Okay, so for section AC. Now let's proceed for section B CB. Okay, section CB. Okay, again I draw the original beam, which is a 13.33, and then here is 26.67. Okay, and then we have distributed load. Okay, distributed load, which is equal to 10 kilonewton per meter. This is point B, this is point C, this is point A. Now we are analyzing for section CB. Okay, again I still analyze the left part of the beam. So for section CB, so I analyze from the left of the beam. So I get this one. Okay, so here is the 13.33, and here is 26.67, and then I have Vx, I have also Mx, and of course I have the distributed load. Okay, so again here will be the distance x. Okay, so for section CB, the x, okay, the distance x is valid from 3 to 4. Okay, because this is a 3, this is 1 meter. So CB, okay, CB here is from 3 meter to 4 meter. Okay, 3 meter to 4 meter. So that's why the x is only valid for 3 to 4 meter. Again, we have the distributed load, so we have to simplify the beam. Okay, we have to convert the distributed load into concentrated load. So again, we have 13.33, and then we have here 26.67, and then we have Vx, we have Mx, and then we have 10x. Okay, why 10x? Because this distance is x. Okay, and remember here is x over 2, because the load 10x is acting at the centroid. Okay, at the centroid of the distributed load. So distributed load is 4 meter. Distributed load is this load is distributed along x. So that's why the 10x is located at the x over 2. Okay, and then don't forget, from here to here is 3 meter. Okay, 3 meter. So from this free body diagram, we can determine the relationship between the shear force and also distance x. Okay, by applying the summation of Fy upward is positive equal to 0. Okay, so from here we can write 13.33, which is here, okay, plus 26.67 minus 10x, okay, minus Vx, okay, Vx equal to 0. So Vx is equal to 40 minus 10x. Okay, so that is the relationship for shear force and also x for section CB. Now we apply the summation of moment at point x, which is here, okay, at this point, equal to 0. Okay, so we can write the mx. Okay, let's say this direction is positive, so mx plus 10x, which is this force, and then multiply by the distance. The distance is x over 2. Okay, x over 2, and then minus 13.33, this force, to the point x. So the distance is x. Distance is x, minus 26.67. Okay, this force to the x. The distance is x minus 3. Okay, so you get from here to here. Okay, so this is x minus 3. Okay, so 26.6 times x minus 3 equal to 0. So mx equal to minus 5x squared plus 40x minus 80. Okay, so there is the relationship between bending moment and also x for section CB. Okay, so we can see this is the linear relationship, this is the quadratic relationship. Alright, so now we already done section for step number 3. Now we proceed to step number 4, which is draw the shear force and bending moment diagram. Okay, shear force and also bending moment diagram. So like usual, let me draw the original beam. Okay, so this is the point A, this is the point C, and this is point B, and then we have distributed load. Okay, distributed load which is 10 kilonewton per meter. So now let me sketch the axis for V, shear force, and also X, and also the other one is M versus X, and here will be the point A, same here, and then here will be the point C and point C, and here will be the point B and point B. Okay, so as we already calculate for section section AC. Okay, where the X is valid for 0 and 3, from 0 to 3 meter. So we have Vx equal to 13.33 minus 10x. Okay, so this is from the analysis of section AC. So Vx equal to 13.33 minus 10x. Okay, so from here, when the x equal to 0, so Vx is equal to 13.33. When the x equal to 3, so Vx is equal to minus 16.67. Okay, so alright, and then so we can plot here when the x equal to 0, which is here. Vx equal to 13.33, so 13.33, which is here. Okay, which is here. And then when the x equal to 3, which is at point C, so this is 3 meter, so Vx equal to minus 16.6. So let's say this is a minus 16.67. So this is the point. Okay, because the relationship here is the linear relationship, so we get the straight line. Okay. Okay. How about the mx? Okay, for the bending moment, so we have the relationship between the bending moment and also x. So mx is equal to 13.33x minus 5x squared. So this is what we already calculated from the previous slide. Okay, for section AC. So when the x equal to 0, so m also equal to 0. When the x equal to 3, so m equal to minus 5. Okay, so from here we can calculate the x equal to 0, which is here. M also equal to 0, that's first point. And then x equal to 3, which is a point C. M equal to minus 5. So somewhere here, minus 5. Okay, so the second point will be here. Okay, so we know that this is the quadratic relationship. Okay, and then minus, this is minus, means the graph should be looks like this. Okay, if you get positive, okay, for x squared you get positive, so the graph will look like this. So for this case, we know that the graph will look like something like this. Okay, something like that. Alright, if you are not sure how what is the shape of the graph, okay, looking at only 2 points, you don't know how to draw the graph, okay, this graph. So you can try calculate the m for other value of x. For example, you try what is the m for when x equal to 1. You can try what is the m for x equal to 2, for example. And then you get the value, and then you can plot for x equal to 1, and then plot for x equal to 2, and so on. Okay, and then you get this shape of graph. And then for section BC, so for section BC, the x is only valid from 3 meter to 4 meter. So you repeat again, whatever you done here, you repeat. So we have the Vx equal to 40 minus 10x. So when the x equal to 3, so m equal to, V equal to 10. And then when the x equal to 4, okay, V equal to 0. So you can plot x equal to 3, okay, which is here, V equal to 10. So let's say this is a 10, so that is the first point. And then when the x equal to 4, which is point B, V equal to 0, so this point. And then this relationship is linear relationship, so you get the straight line. So that is your shear force diagram. Then we have the relationship for bending moment diagram, where the mx is equal to, bending moment relationship, okay, which is the mx equal to minus 5x squared plus 40x minus 80. So same thing when the x equal to 3, so mx equal to minus 5. When the x equal to 4, m equal to 0. So x equal to 3, m equal to minus 5, which is here, and then x equal to 4, which is point B, m equal to 0. Okay, and then you see here, this is the minus quadratic. Okay, minus quadratic. So your graph is look like this. Okay, so you get like that. Okay, so in the slide, I do mistake on for the graph 4 point CB. So please check. So this should be should be the shape for curve CB. Okay, so that's all. This is a shear force diagram. This is the bending moment diagram. So from here, what we can see that the maximum value for the shear force is 16.67, which is at the point C, and then the maximum value for bending moment is somewhere in between A and C. Okay, you can calculate what is the value. Basically, you can calculate this value. So from this maximum value, you can further analyze what is the shear stress. Okay, maximum shear stress. Okay, because you already get the shear force, you can calculate the shear stress. Okay, equal to V over A, or VQ over IT. Okay, later. And then from maximum bending moment, you can calculate the maximum normal stress, which is equal to MC over I. Okay, that's it for example number 2. Thank you very much. Good luck. Thank you.